This covers Chapter 5, and in Chapter 5 what you're looking at is probability distributions. We're going to be looking at random probability distributions and then two specialty kinds. One's called binomial and the other one is called Poisson. So we'll start first by talking about random variables. A random variable is a numerical description of the outcome of an experiment, nothing earth-shattering. A discrete random variable may assume either a finite number of values or an infinite sequence of values. What that means specifically is that a discrete variable is a numerical description of the outcome. It's always a whole number, and that's what the key is. An example of that would be if you were asked to count the number of birds in a tree. The number you would get is something between 0 and an infinity, and it would be a whole number. You wouldn't get 3.5, 10.5, 12 3/4 birds. It would be a whole number. On the other hand, a continuous random variable can assume any numerical value in an interval. And the difference is when you're looking at continuous variables, it could be described as a fraction. In other words, here is a case where you've got 6 people in a race and the guy in red is ahead. Maybe his time to finish that race was 10.25 minutes or 10.47 minutes or whatever. The point being that it would not have to be a whole number. When you're looking at problems of distance or time, typically those would be continuous variables. The flight time, for example, between Miami, Florida and New York City, maybe it's 2 hours and 20 minutes, 2 hours and 23 minutes, 2 hours and 10 minutes, whatever. The time does not have to be a whole number. When we're looking, though, at discrete random variables, a good example might be shown by this JLL appliances. A discrete variable with a finite number. In this small electronics store, let's let X equal the number of TVs sold in the store in one day. And in this case, X can take on the value of 0 to 4, 5 different values. We could also count the customers arriving in the store, but there is no finite upper limit on the number who might arrive. The probability distribution then for a random variable describes how probabilities are distributed over the values of that random variable. We can describe the discrete probability distribution with a table, a graph, or actually an equation. The probability distribution is defined by a probability function denoted by f of x, standing for the function of x, which provides the probability for each value of the random variable. The required conditions for a discrete probability are that the function of x is equal to or greater than 0. And the total of all of the outcomes that are possible is going to always come out as 1. The probability of an event is a number always between 0 and 1. So the total of all of the possibilities is 1. It's important that you realize when you're looking at probabilities, that's pretty much all that you're going to come up with, that the total of all of the possibilities equal 100%. All of the possible answers equal 100% or 1.00 of the probabilities. Discrete uniform probability distribution. The discrete uniform probability distribution is the simplest example of a discrete probability distribution given by a formula. The discrete uniform probability function is that the function of x is equal to 1 divided by n, where n equals the number of values the random variable may assume. All of the values divided by 1 is the answer that you would get. The values of the random variables in this case are all equally likely to occur. And, what would it be if you were flipping a coin? Well, it's heads or tails. If you were rolling a die, it would be 1 out of 6 to get any one of the numbers. 6 choices. The probability of getting any of them is all the same. They're all equal. When we talk about the expected value and the variance, the expected value, or the mean of a random variable, is a measure of its central location. And the formula sometimes is a little scary, but it shouldn't be. The expected value of x is equal to u, the mean. That's what the expected value is. That large figure looking like an E stands for the total of x, each of the x's times the function of x. You add them all up, you get the expected value. The variance summarizes the variability in the values of a random variable. And again, the formula is starting to get a little bit more complicated. But as you'll see when we do the calculations, this is easy for us to do when we're using Excel. By the way, after you get the variance, the standard deviation, which is signified by the Greek letter O, is defined as the positive square root of the variance. Discrete probability distributions. Here's back to our TV store. Using past data on the TV sales, a tabular representation of the probability distribution for TVs was developed. Remember what our example showed. The units sold in a day were somewhere between 0 and 4. If we looked at a period of time, there was 80 days we didn't sell any TVs, and there was 50 days we only sold one, 40 days we sold two, and so on for the rest of the list. We total this column up, and when we do that, we see that the total for that column is 200. Next thing we want to do is we want to figure out what the function of x is. And for us to do that, what we're going to do is we're going to divide each one of those number of days by 200. And when we do that, the number shown in green is what we're going to develop. We've totaled this column to get the 200, and then we're going to divide each number by that total. So when we divide 80 by 200, that's where we get our 0.4. And the same thing is true with all of the numbers in the list. When we get through and we total up the green column, the total should and will equal 1, because that's 100% of all of the possibilities. Okay, next column, and you can see at the heading, we're asked to multiply x times the function of x. Well, you see that the first column in the units sold, that's x. The function of x is the number that we just developed. So we're going to multiply x times the function of x. In the first case, that's 0 times 0.4. That's going to give us 0. Anything times 0 is 0. We're going to do the same thing for every one of those rows. And then, in order to get the expected value signified by u, we're going to add up the total of the x times the function of x column. And when we do that, you see that the expected value is 1.20. The next column, when we're solving this problem, is x minus u. X we know is 0, and U we just developed is 1.20. So 0 minus 1.2, that's where we get our negative 1.2. 1 minus 1.2 gives us negative 0.20, and so on down the whole list. The column after that is x minus u squared. Well, that's easy enough. We're going to take negative 1.2 times itself, the square, and we're going to get 1.44. Similarly, when we take negative 0.2 and we square that, we get 0.04, and so on down that list. For the last column, we're going to have x minus u squared, which is the previous column, that's that 1.44, times the function of x. And we look at the function of x in this first row, and we see it's 0.4. And when we multiply those two together, we get 0.576. We're going to do the same thing for every one of those columns. Any one of the rows in that column, excuse me. When we total that up, we see that the variance, because the total of this column equals the variance, in this case, it's 1.660. In order to get the standard deviation, we take the square root of that number. And the square root of 1.660 gives us 1.2884. So the first part of what it is that we're trying to do on discrete probability distributions has been covered by the things that we have just reviewed. So I'm going to stop this part of the lecture now, and then we'll come back in a minute or so after you've had a chance to see this, and we'll look at some specifics for binomial distribution and Poisson distribution, which will finish the items that are covered in this chapter.